And now in this lecture we'll answer two questions. In the first question we find out the area of this trapezoid ABCD, and in the second question we find out the area of this quadrilateral ABCD in two different methods. So we start with the first question. In the drawing we have trapezoid ABCD. The circle is inscribed by trapezoid ABCD, or trapezoid ABCD blocks this circle. In addition, you know that side DA is equal to side CB equals to 41 units in its length, side AB equals to 50 units in its length. Again, our task is to find out the area of this trapezoid ABCD. So first of all, what is a trapezoid? A trapezoid is a quadrilateral with one pair of parallel sides. This is trapezoid ABCD. Side DC is parallel to side AB, and therefore quadrilateral ABCD is a trapezoid because it has one pair of parallel sides. The height is h, its raised 9 degrees, 52 bases. And they have this trapezoid ABCD. If we define the length of side DC as A and the length of side AB as B, then they have this trapezoid ABCD equals to the sum of its two parallel bases, that is actually A plus B, times the height h over 2. Repeat again, the area of trapezoid ABCD, or the area of any trapezoid, equals to the sum of its two parallel bases times the height over 2. And the height must raise 9 degrees with the two parallel bases. So first of all, in order to find out the area of this big trapezoid ABCD, we will define the point of tendency of tangent DA with this circle. This point is point E. And we define the point of tendency of tangent DC with this circle. This point is point F. Likewise, we define the point of tendency of tangent CB with this circle. This point is point G. We define the point of tendency of tangent AB with this circle. This point is point H. So here we can implement rule 2. I repeat quickly rule 2. According to rule 2, the lengths of two tangents from a common start point to a circle are equal. So in the drawing we have a circle. This is the common start point, point P. From this common start point, point P, we have two tangents to this circle. Tangent PA and tangent PB, and according to this rule 2, they are equal to each other. That is to say, PA equals to PB. So we can actually implement rule 2 in our drawing. Because in our drawing, we focus on this common start point, point D. From this common start point, point D, we have two tangents to this circle, tangent DF and tangent DE, and according to rule 2, they are equal to each other. That is to say, DF equals to DE. So if we define the graph of DF as A, then the graph of tangent DE must be also equal to A, because they are equal to each other according to rule 2. Likewise, we focus on this common start point, point C. From this common start point, point C, we have two tangents to this circle, tangent CF and tangent DG, and according to rule 2, they are equal to each other. That is to say, tangent CF equals to tangent CG. So if we find the length of tangent CF as B, then the length of tangent CG must be also equal to B, because they are equal to each other according to rule 2. Likewise, we focus on this common start point, point A. From this common start point, point A, we have two tangents to this circle, tangent AE and tangent AH. And according to rule 2, they are equal to each other. That is to say, AE equals to AH. A equals to AH. So if we define the length of tangent AE as C, then the length of tangent AH must be equal to 3 units in its length. So they are equal to each other according to rule 2. And finally, focus on this common start point B. From this common start point B, we have two tangents to this circle. Tangent BG and tangent BH. And according to all two, they are equal to each other. That is to say, BG equals to BH. So if we define the length of tangent BG as D, then the length of tangent BH must be also equal to D because they are equal to each other according to all two. So what is the length of side DA plus the opposite side CB? DA plus the opposite side CB in total equals to A plus B plus C plus D. What is the length of side DC plus the opposite side AB? DC plus AB, DC plus AB equals to A plus B plus C plus D. So if you found out that both those two expressions are equal to A plus B plus C plus D, therefore they are equal to each other. That is to say, DA plus CB equals to DC plus AB. So as you know, if you found out that DA plus CB equals to DC plus AB. DA equals to 41 according to what is given as the question, plus CB also equals to 41. So in this side of the equation we have 41 plus 41 equals to DC. DC is the missing side, so we leave it as it is, so it is DC plus AB. AB equals to 50 units in its length according to what is given as the question. So in total we should found out that 41 plus 41, that is 82, equals to DC plus 50. Here we subtract 50 from this equation and finally get that the missing side DC is equal to 82 minus 50 is 32. So the missing side DC equals to 32 units in its length. This is the missing side DC. This is equals to 32 units in its length. In the next step, we will do a construction. That is to say, from point D, we will do perpendicular on AB. Again, from point D, we will do perpendicular on AB. So okay, this angle equals to 90 degrees and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point D and AB. This point is point N. The next step we will do another construction, that is to say from point C we will do perpendicular on AB. Again from point C we will do perpendicular on AB. So okay, this angle equals to 90 degrees and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point C and AB. This point is point J. We know that ABCD is a trapezoid. In trapezoid ABCD, side DC is parallel to side AB. Again, in trapezoid ABCD, side AC is parallel to side AB. So in the domain we have those two angles that are defined as one-sided interangles, and they are located between the parallel lines DC and AB. And according to Rule 13, the sum of those two one-sided interangles that are located between the parallel lines DC and AB is equal to 180 degrees. So I can click on Rule 17. According to Rule 17, the sum of one-sided interangles that are located between two parallel lines is equal to 180 degrees. In the drawing we have line A is parallel to line B, and the red line C cuts those two parallel lines A and B. Those two angles, alpha and beta, are defined as one-sided interangles. They are located between the two parallel lines A and B. And according to this Rule 17, the sum of those two one-sided interangles, that is say alpha plus beta, is equal to 180 degrees because of the fact that they are located between the parallel lines A and B. So we can implement Rule 17 in our domain. Because in our domain we have those two one-sided interangles that are located between those two parallel sides DC and AB, and therefore the sum of those two one-sided interangles must be equal to 180 degrees. So 90 degrees plus this missing angle, that is actually angle DCJ. In total, they must be equal to 180 degrees according to Rule 17. So here we'll subtract 90 degrees from this equation, and finally we get the missing angle DCJ. This is the missing angle DCJ is equals to 180 degrees minus 90 degrees is 90 degrees. So the missing angle DCJ is the right angle. Likewise, the sum of those two one-sided interangles that are located between the parallel lines CD and AB must be equal to 180 degrees according to Rule 17. So write it down. This angle equals to 90 degrees plus this missing angle, that is actually angle CDN. In total, the sum of those two angles must be equal to 180 degrees according to the same rule, Rule 17. So here we subtract 90 degrees from the equation, and finally get that the missing angle CDN is equal to 180 degrees minus 90 degrees is 90 degrees. So the missing angle CDN equals to 90 degrees in its size according to Rule 17. This is the missing angle CDN that is equal to 90 degrees in its size. So in quadrilateral CDNJ, in this quadrilateral we have 4 right angles, and therefore quadrilateral DCNJ is right angle. Because it has 4 right angles. But we also know that the opposite sides of rectangle are equal to each other. So in the big rectangle DCJN, side DC must be equal to the opposite side NJ. But DC is 32, therefore the opposite side NJ must be also equal to 32 units in its length. According to the sum rule, in the sum after DCJN, side CJ must be equal to the opposite side DN. So CJ equals to DN. In the next time we focus on those two right angles, the right angle CJB and the right angle DCN. The hypotenuse of this right angle is 41 and the hypotenuse of this right angle is also 41. Therefore, the hypotenuses of those two right angles are equal to each other. Likewise, those two sides are also equal to each other. And this first missing side must be also equal to each other in both right angles. So I prove that those two sides are also equal to each other in those two right angles. So I copy this right angle in a new page and I prove that those two sides are also equal to each other. That is to say side JB equals to side AN. So those are the two right angles that are coming from the original domain. So I define the hypotenuse DA as y, and therefore the other hypotenuse CB must be also equal to y because they are equal to each other according to what is given as the question. They are both equal to 41 units, therefore they are equal to each other. In addition, those two sides are also equal to each other. So if this side is x, then this side must be also equal to x because they are equal to each other. So in this right angle ADN, according to the Pythagoras theorem, y squared, that is the square of the hypotenuse, equals to x squared plus an squared. Again, y squared equals to x squared plus an squared. If subtracting x squared from this equation, you find out that y squared minus x squared equals to an squared. Again, y squared minus x squared equals to an squared. If we take root of this equation, you find out that the missing side an equals to the square root of y squared minus x squared. Likewise, we did the same process here. This right angle, according to the Pythagoras theorem, this right angle CJB, y squared equals to x squared plus JB squared. Again, y squared equals to x squared plus JB squared. If subtract x squared from this equation, if I found out that JB squared equals to y squared minus x squared. If we take root of this equation, if I found out that JB, the left of side JB is square root of y squared minus x squared. But an also equals to the square root of x squared minus x squared, and therefore those two sides are equal to each other. So side an is equal to side CB. Therefore in total we found out that those two right angles can go into each other according to side rule. Those two sides are both equal to y, therefore they are equal to each other. Those two sides are both equal to x, therefore they are equal to each other. And finally, side an equals to side JB. Therefore, those two right angles can go into each other according to side rule. So, write it down. We actually found out that the right angle DNA congruent, this is the sign of congruent, to the right triangle CJB according to side rule. And from the fact that those two right angles can go into each other, we derive that side AN equals to side JB. AN equals to JB. According to the rule that corresponding sides in congruent triangles are equal to each other. Those two triangles can go into each other, therefore the two corresponding sides, that is to say AN and JB, must be also equal to each other and their lengths. So if we define the length of side AN as x, then the length of side JB must be also equal to x because they are equal to each other. AB equals to 50 units in its length. AB in total equals to x plus 32. Already know. AB in total equals to 50 units in its length. According to what is given in the question, that is it, and it is also equals to x plus 32. So in total we get that 50 equals to 32 plus 2x. Here we subtract 32 from the equation and get that 50 minus 32 is 18, so 18 equals to 2x. Here we divide this equation by 2 and finally get that x equals to 18 over 2 is 9, so x equals to 9 units in its length. X equals to 9 units in its length. So if you found out that the length of side AN is equals to x equals to 9 units, and side JB this is also equals to x equals to 9 units in its length. In the next step, I'll copy the right triangle CJB in a new page and we will implement on this right triangle CJB the Pythagoras theorem in order to find out the length of side CJ. Here by PT the abbreviation for Pythagoras theorem. So actually, this is the right triangle CJB that is according to the original drawing. This right triangle CJB according to the Pythagoras, according to the Pythagoras theorem, and in a right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. So in the right triangle CJB, CB squared, that is the square of the hypotenuse, equals to JB squared plus CJ squared. So on the norm, CB squared, that is the square of the hypotenuse, equals to CJ squared plus JB squared. CB is 41, therefore CB squared is 41 squared, that is 1681, and it is equals to CJ squared. CJ is the missing side, so we leave it as it is, so it is CJ squared plus JB squared. JB is 9, therefore JB squared is 9 squared, that is 81. So in total we found out that 1681 equals to CJ squared plus 81. Here we subtract 81 from this equation and finally get that CJ squared equals to 1681 minus 81 is 1600. So CJ squared equals to 1600. Here we take out all of this equation and finally get that CJ, the missing side CJ equals to the square root of 1600, it is 40. So CJ equals to 40 units in its length. This is side CJ, this is equals to 40 units in its length. CJ is actually also the height of the trapezoid ABCD because it creates 90 degrees with the base AB, and it also creates 90 degrees with the base CD. Therefore, CJ is the height of trapezoid ABCD. Our task is to find out the area of this trapezoid ABCD. So there of trapezoid ABCD, according to the formula that I presented to you in the beginning of the lecture, the area of trapezoid ABCD is equal to the sum of its two parallel bases, that is actually DC plus AB, times the height CJ over 2. But again, the area of trapezoid ABCD equals to the sum of its two parallel bases, that is DC plus AB, times the height CJ over 2. DC is 32 plus AB is 50 times the height CJ, that is 40, divided by 2. So total, we found out that the area of trapezoid ABCD equals to 32 plus 50 times 40 over 2. 32 plus 50 is 82, and 40 over 2 is 20. So total, the area of trapezoid ABCD equals to 82 times 20, that is 82 times 20, that is actually 1640 square units in its size. This is the answer to the question. I repeat again, we actually found out that the area of this trapezoid ABCD is equal to 1640 square units in its size. So we finish with the first question. In the next step, I will present you the second question, and we solve the second question by using two different methods. In the second question, our task is to find out the area of this quadrilateral ABCD. So in the domain you have quadrilateral ABCD. This is angle ABC, that is right angle. This is angle ADC, this is also equals to 90 degrees in its size. This is angle BCD, this is equals to 45 degrees in its size. This is side AB, this is equals to 10 units in its length. This is side DC, that is equals to 25 units in its length. Again, our task is to find out the area of this quadrilateral ABCD. So, first of all, we will do a construction. That is to say, from point B, we will draw perpendicular on DC. Again, from point B, we will draw perpendicular on DC. So actually, this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point B and DC. This point is point N. In the next step, we will do another construction, that is to say, from this point, point A, we will draw perpendicular on BN. Again, from point A, we will draw perpendicular on BN. So actually, this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point A and BN. This point is point M. By doing those construction, we have gathered there quadrilateral AM and D. Inside quadrilateral AM and D, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees, so 270 degrees plus the size of this fourth facing angle, in total they must be equal to 360 degrees according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. And therefore this fourth facing angle must be equal to 90 degrees in its size. So inside quadrilateral AM and D, we have 4 right angles, therefore according to 5, any quadrilateral that has 4 right angles must be this rectangle plus the square. So we write to quadrilateral AM and D is rectangle because it has 4 right angles. So if it's on quadrilateral AM DN is rectangle according to rule 5 because it has 4 right angles. define the length of side AM as A. We know that the opposite sides of a rectangle are equal to each other. So in rectangle AM and D, side AM must be equal to the opposite side DN. But AM is A, therefore the opposite side DN must be also equal to A units in its length. What is the length of this line segment NC? NC equals to DC minus DN. Again, NC equals to DC minus DN. So write it down. NC equals to DC minus DN. So NC equals to DC. DC is 25. Minus DN. DN is A. So in total, NC equals to 25 minus A units in its length. This is line segment NC. This is equals to 25 minus A units in its length. In the next step, we'll focus on this right triangle NBC. In the right triangle NBC, this angle equals to 90 degrees, this angle equals to 45 degrees, and therefore this part missing angle must be equal to 45 degrees in its size. Y equals 45 degrees plus 45 degrees is 90 degrees. In 90 degrees plus 90 degrees, it is equal to 180 degrees. That is the sum of the angles in any triangle. We have the rule that in front of equal angles in the triangle, there are equal sides. So if we focus on the right triangle BNC, in front of those two equal angles, we have those two sides that must be equal to each other and their lengths. But NC is 25 minus A, therefore BN must be also equal to 25 minus A units in its length. So this is side BN. This is equals to 25 minus A units in its length. This is the big angle ABC, equals to 90 degrees in its size. This is angle NBC, that is equals to 45 degrees in its size. And therefore this missing angle must be equal to 90 degrees minus 45 degrees. Again, this missing angle must be equal to the big angle, that is the right angle, plus 45 degrees. 90 degrees minus 45 degrees is 45 degrees. So this missing angle equals to 45 degrees in its size. So in the small right triangle BMA, we have this angle equals to 45 degrees, this angle equals to 90 degrees, and therefore this first missing angle must be equal to 45 degrees in its size, according to the same rule that the sum of the angles in any triangle is equal to 180 degrees. So in the right small triangle MBA, in front of those two equal angles, we have those two sides that must be equal to each other and their length. But AM is A, therefore BM must be also equal to A units in its length. So BM equals to A units in its length. So what is the length of this? Actually, we only found out that BM equals to 25 minus A. So what is the length of MN? From the drawing it is very easy to see that MN in total equals to BN minus BM. Repeat again. This is the missing side MN that equals to BM minus BM. Again, MN equals to BN minus BM. So MN in total equals to BN is 25 minus A minus BM. BM is A. So 25 minus A is 25 minus 2A. So total MN equals to 25 minus 2A units in its length. So here this is the missing side MN, that is equals to 25 minus 2A units in its length. So in the rectangle in rectangle AMND, side MN must be equal to the opposite side AD. According to the rule, the opposite sides of a rectangle are equal to each other. But MN is 25 minus 2A, therefore the opposite side AD must be also equal to 25 minus 2A units in its length. So it is now AD equals to 25 minus 2A units in its length. In the next step, we will implement the Pythagoras theorem of this small right triangle ABM. So I copy the small right triangle ABM in the new page, and we will implement on it the Pythagoras theorem. Here by PT is the progression of Pythagoras theorem. So actually, this is the right small triangle ABM, this is the copy from the original theorem. This small right triangle ABM, according to the Pythagoras theorem, BA squared, this is the square of the hypotenuse, equals to BM squared plus MA squared. BA is 10, therefore BA squared is 10 squared, that is 100. And it is equals to BM squared. BM is 8, therefore BM squared is 8 squared. Plus AM squared. AM is also 8, therefore AM squared is 8 squared. 8 squared plus 8 squared is 2A squared, so in total we should find out that 100 equals to 2A squared. It again, 100 equals to 2A squared. Our task is to find out the area of this quadrilateral ABCD. This is quadrilateral A, B, and D. In quadrilateral A, B, and D, we have side MN is parallel to the opposite side AD. According to the rule, that the opposite sides of a rectangle are parallel to each other. But BN is a third line because angle BMN is equal to 180 degrees in size, and we know that any angle that is equal to 180 degrees in size, it is defined as a third line. Therefore, BN is a third line, but we know that part of the third line BN, that is MN, is parallel to AD. So if part of a third line is parallel to another third line, then the third line itself, BN, must be also parallel to AD. So in quadrilateral A, B, and D, side BN is parallel to side AD, and therefore quadrilateral A, B, and D is a trapezoid. So it is done. If you found out that quadrilateral A, B, and D is a trapezoid, because it has one pair of parallel sides. Side BN is parallel to side AD. So quadrilateral A, B, and D is a trapezoid. What is the area of trapezoid ABCD? Trapezoid A, B, and D. This trapezoid A, B, and D. The area of trapezoid A, B, and D equals to the sum of its two parallel sides, that is BN plus AD. times the height AM over 2. And again, the area of this trapezoid A, B, and D equals to the sum of its two parallel sides. The sum of its two parallel sides, that is BN plus AD times the height AM over 2. BN is 25 minus A plus AD. AD is 25 minus 2A times the height AM. AM is A divided by 2. So today we found out that the area of this trapezoid A, B, and D is equal to 25 minus A plus 25 minus 2A times A over 2. 25 plus 25 is 50. Minus A minus 2A is minus 3A times A over 2. So in total we found out that the area of trapezoid A, B, and D is equal to 50 minus 3A times A over 2. Here we'll open the brackets and we get that 50 times A is 50A, minus 3A times A is minus 3A squared over 2. So in total we found out that the area of this trapezoid A, B, and D is equal to 50A minus 3A squared over 2. Again, the area of this trapezoid A, B, and D equals to 58 minus 3A squared over 2. Our task is to find out the area of this quadrilateral ABCD. From the drawing it is very easy to see that the area of this quadrilateral ABCD in total is equals to the area of this trapezoid A, B, and D plus the area of this right triangle B and C. So I write down the area of this big quadrilateral ABCD in total it is equals to the area of this trapezoid A, B, and D minus the area of this right triangle B and C. Again, we found out that the area that we are looking for in this question, that is the area of this quadrilateral ABCD, is equal to the area of trapezoid A, B, and D plus the area of this right triangle B and C. So repeat again, the area of quadrilateral ABCD in total equals to the area of trapezoid A, B, and D plus the area of the right triangle B and C. But we already found out that the area of trapezoid A, B, and D is equals to 58 minus 3A, 58 minus 3A squared over 2. So write it down. If we found out that the area of trapezoid A, B, and D is equal to 58 minus 3A squared over 2 minus the area, plus the area of the right triangle B and C. The area of this right triangle B and C equals to the base NC times the height BN over 2. And again, the area of this right triangle B and C in total equals to the base NC times the height BN over 2. So we have here 58 minus 3A squared over 2, and we have plus NC times BN. NC is 25 minus 8 times Bn. Bn is also 25 minus A, so NC times Bn is 25 minus A squared. So in total, there are on top of the B and D equals, there of course the other ABCD equals to 58 minus 3A squared plus 25 minus A squared over 2. So here we'll open the brackets and we get that the area of for the other ABCD in total will be equal to 58 minus 3A squared. We have 25 minus A squared. 25 minus A squared equals to 25 squared, this is 625, plus A squared, minus 2 times 25 times A, this is minus 58, divided by 2. So here we have 58 minus 58 is 0, so those two expressions will get cancelled. And we're left only with 625 minus 3A squared over 2. And again, we should know that the area of this big quadrilateral ABCD equals in total to 625. And we have minus 3A squared plus A squared is minus 2A squared. So in total, the area of quadrilateral ABCD equals to 625 minus 2A squared divided by 2. But we already found out that 2A squared equals to 100. Therefore, we substitute 2A squared here by 100, and we get that the area of a quadrilateral ABCD in total will be equal to 625 minus 2A squared. 2A squared is 100, so we substitute 2A squared by 100, and we get that in total the area of quadrilateral ABCD equals to 625 minus 100 is 525 over 2. 525 over 2 is 262.5 square meters in size. So, again, I should found out that the area that we are looking for in this question, that is the area of this quadrilateral ABCD, is equal to 262.5 square meters in its size. So we finish with the first method. In the next step, I present to you how to find out the area of this quadrilateral ABCD according to the second method. In the second method, we will do a construction. That is to say, we will extend side DA and side CB of this quadrilateral ABCD by a straight line until they touch each other. So here, this is the touching point. We define the touching point of the extended side DA with the extended side CB. This point is point M. By doing this construction, we're going to do the big right triangle MDC. In the big right triangle MDC, this angle equals to 90 degrees, this angle equals to 45 degrees, and therefore this first missing angle must be equal to 45 degrees in size. According to the rule that the sum of the angles in any triangle is equal to 180 degrees. 45 degrees plus 45 degrees is 90 degrees, and 90 degrees plus 90 degrees, it is equal to 180 degrees. That is the sum of the angles in any triangle. We have the rule that in front of equal sides in front of equal angles in the triangles, they are equal sides. So if we relate to the big right triangle MDC, in front of those two equal angles, we have those two sides that are equal to each other. But side DC is 25, therefore side MD must be also equal to 25 units in its length. So MD equals to 25 units in its length. MC is the hypotenuse of the big right triangle MDC. So MC is hypotenuse. MC is an hypotenuse. It is absolutely a straight line. So if you focus on the left side of the straight line MC at point B, here the sum of the angles must be equal to 180 degrees according to rule 3. Rule 3 says that the sum of the angles on one side of a straight line is equal to 180 degrees. So which angles we have at the left side of the straight line MC at point B? We have this angle that is right angle plus this missing angle. Total the sum of those angles must be equal to 180 degrees according to rule 3. Therefore this missing angle must be equal to 90 degrees in its size. So in the small right triangle MBA, this angle equals to 90 degrees, this angle equals to 45 degrees, and therefore this first angle must be equal to 45 degrees in its size, according to the rule that the sum of the angles in any triangle is equal to 180 degrees. So this angle must be equal to 45 degrees in its size. In the right small triangle MBA, in front of those two equal angles, we have those two sides that must be equal to each other in their lengths. But side AB is 10 units, and therefore side MB must be also equal to 10 units in its length. So what is the area of quadrilateral ABCD? This is the area that we are looking for. Actually, from the drawing, it is very easy to see that the area of this quadrilateral ABCD is equal to the area of the big right triangle MDC minus the area of this small right triangle MBA. But again, the area of this quadrilateral ABCD, in total it must be equal to the area of the big right triangle MDC minus the area of the small right triangle MBA. The area of the big right triangle MDC equals to the base DC times the height dm over 2. But again, the area of this right triangle MDC total equals to the base DC times the height dm over 2. Minus the area of this right triangle MBA. The area of this right small triangle MBA equals to the base AB times the height MB over 2. And again, the area of this small right triangle MBA is equals to the base AB times the height MB over 2. So total, the area of this quadrilateral ABCD equals to DC is 25 times DM is also 25 divided by 2 minus AB is 10 times BM is also 10 divided by 2. So in total, we found out that the area of this quadrilateral ABCD equals to 25 square minus 10 square over 2. 25 square is 625 minus 10 square is minus 100 divided by 2. 625 minus 100 is 525 divided by 2. 525 over 2 is 262.5 square units in its size. And again, we should find out that the area that we are looking for this question, that is the area of this quadrilateral ABCD, in total it is equals to 262.5 square units in its size. So we finish with the first. We finished with the second method of the second question. So in the next step, I will start the lecture. We'll start with the first question, of course. In the first question, our task is to find out there are this trapezoid A, B, C, D. So, what is a trapezoid? A trapezoid is a quadrilateral with one pair of parallel sides. Repeat again. A trapezoid is a quadrilateral with one pair of parallel sides. So, we know that the area again, a trapezoid is quadrilateral with one pair of parallel sides. So this is trapezoid ABCD. Side DC is parallel to side AB, and therefore quadrilateral ABCD is a trapezoid. If we define the length of side DC as A and the length of side AB as B, then the area of this trapezoid ABCD equals to the sum of its two parallel bases. This is actually A plus B times the height edge over 2. So, in the first step, I presented to you rule 2 and implemented rule 2 in our drawing. According to rule 2, the lengths of two tangents from a common standpoint to a circle are equal. So in the drawing we have a circle. This is the common standpoint point P. From this common standpoint point P we have two tangents to this circle. Tangent PA and tangent PB, and according to rule 2 they are equal to this rule 2 they are equal to each other. That is to say PA equals to PB. So we can actually implement rule 2 in our drawing. Why? Because in our drawing, if we focus on this common standpoint point D, from this common standpoint point D, we have two tangents to this circle, tangent DF and tangent DE. And according to rule 2, they are equal to each other. That is to say DF equals to DE. So if we define the length of DF as A, then the length of DE must be also equal to A, because they are equal to each other according to rule 2. Likewise, if we focus on this common standpoint point C, from this common standpoint point C, we have two tangents to this circle, tangent CF and tangent CG, and according to rule 2 they are equal to each other. That is to say, CF equals to CG. So if we define the length of tangent CF as B, then the length of tangent CG must be also equal to B, because they are equal to each other according to rule 2. Likewise, if we focus on this common standpoint point B, from this common standpoint point B, we have two tangents to this circle, tangent VG and tangent VH, and according to rule 2 they are equal to each other. That is to say VG equals to VH. So if we define the length of tangent VH as D, then the length of tangent VG must be also equal to B units in its length. Finally, if we focus on this common standpoint point A, from this common standpoint point A, we have two tangents to this circle, tangent AE and tangent AH. And according to rule 2 they are equal to each other. That is to say AE equals to AH. So if we define the length of tangent AE as C, then the length of tangent AH must be also equal to C units in its length, because they are equal to each other according to rule 2. So what is the length of side DA plus the opposite side CB? DA plus CB equals to A plus B plus C plus D. Repeat again. DA plus the opposite side CB in total equals to A plus B plus C plus D. Likewise, what is the length of DC plus AB? DC plus AB also equals to A plus B plus C plus D. And again, DC plus AB also equals to A plus B plus C plus D. and because of the fact that those two expressions are both equal to a plus b plus c plus d, they must be equal to each other. That is to say, dA plus cb equals to dc plus ab. dA is 41, cb is also 41, and this is the missing side, and ab is 50. So in total, 41 plus 41 is 82. So 82 equals to dc plus 50. We subtracted 50 from this equation. If I found out that dc, the missing side dc equals to 82 minus 50, that is 32. This is the missing side dc, that equals to 32 units in its length. In the next step, we did the construction, that is to say, from point D, we do perpendicular on AB. Again, from point D, we do perpendicular on AB. So this angle was 90 degrees, and this angle also was 90 degrees according to our construction. We define the touching point of the perpendicular from point D and AB. This point is point N. Likewise, we did another construction, that is to say, from point C, we do perpendicular on AB. So this angle was 90 degrees, and this angle also was 90 degrees according to our construction. We define the touching point of the perpendicular from point C and AB. This point is point J. So we know that ABCD is a trapezoid. In trapezoid ABCD, side DC is parallel to side AB. So those two angles are defined as one-sided interangles and are located between the parallel DC and AB. And therefore the sum of those two angles must be equal to 180 degrees according to rule 17. So this angle is a right angle, that is to say it is 90 degrees, plus the missing angle, that is angle CDN. In total, the sum of those two angles must be equal to 180 degrees according to rule 17. Here we subtract 90 degrees from this equation. If I found out that the missing angle CDN equals to 90 degrees in size. Likewise, those two angles are also defined as one-sided interangles and are located between the parallels DC and AB. And therefore, the sum of those two angles, the sum of those two one-sided interangles that are located between the parallels DC and AB must be equal to 180 degrees according to rule 17. So 90 degrees plus this angle, this is actually angle DCJ. In total, they must be equal to 180 degrees according to rule 17. Here we subtract 90 degrees from this equation, and finally found out that this is the missing angle DCJ. This equals to 180 degrees minus 90 degrees is 90 degrees. So this angle equals to 90 degrees in its size. So in total, in quadrangle DCJN, we have 4 right angles, and therefore quadrangle DCJN is right angle, because it has 4 right angles. But we also know that the opposite sides of rectangle are equal to each other. So rectangle DCJN, side DC must be equal to the opposite side NJ. But DC is 32, therefore the opposite side NJ must be also equal to 32 units in its length. Likewise, according to the sum rule, the sum of the DCJN, side DJ must be equal to the opposite side DN. Those two sides are equal to each other. Okay, so, and we know that if we focus on those two right angles, this is to say right angle DAN and this right angle CJB. The hypotenuse CB of this right angle CJB is equal to the hypotenuse DA of this right angle DAN. Why? Because both of them are equal to 41 units in its length, and therefore they are equal to each other. Those two sides are equal also to each other. So in the next step, I copy those two right angles in an equation and we prove that side JB of the right angle CJB is equal to side AN of the right angle DNA. So actually, those are the two right angles that are going from the original drawing. This right angle DNA, so the hypotenuse DA is Y, and therefore the hypotenuse CB must be also equal to Y because they are equal to each other. Likewise, DN is X, therefore CJ must be also equal to X because they are equal to each other. So in this right angle DNA, according to the Pythagoras theorem, Y squared equals to X squared plus AN squared. Again, Y squared equals to X squared plus AN squared. If subtracted X squared from the equation, if I found out that AN squared equals to Y squared minus X squared. If we took out of the equation, if I found out that the length of AN is equal to Y squared minus X squared. Likewise, we repeat it on the same process here in this right angle CJB. JB according to the Pythagoras theorem, y squared equals to x squared plus JB squared. Again, y squared equals to x squared plus JB squared. If subtracted x squared from the equation, if I found out that JB squared equals to y squared minus x squared. So here we took out of this equation, if I found out that JB also equals to the square root of y squared minus x squared. Exactly like AN, this is also equals to y squared minus x squared. And because of the fact that those two sides are both equal to the same expression, they must be equal to each other. That is to say, AN equals to JB. So, those two rectangles can go into each other according to side rule. That is to say, those two sides are both equal to y, therefore they are equal to each other. In addition, those two sides are both equal to x, therefore they are equal to each other. And finally, side AN equals to side JB. Therefore, those two rectangles can go into each other according to side rule. And again, if you found out that the right triangle DNA can point, this is the sign of can point, to the right triangle CJB according to side rule. And from the fact that those two right triangles can point to each other, we will derive that side AN equals to side JB. Again, side AN equals to side JB according to the rule that corresponding sides that can point triangles are equal to each other. Those two right triangles can go into each other, therefore the two corresponding sides, that is to say AN and JB, must be also equal to each other in their length. So AN equals to JB. So if we define AN as x, then JB must be also equal to x because they are equal to each other. AB in total is 50 according to what is given in the question. But AN, that is 50, is equals to x plus 32 plus x. So again, AB is equals to 50, in total it is equals to x plus 32. So 50 equals to x plus x is 2x plus 32. So 50 equals to 32 plus 2x. If subtract the 32 from the equation, if I found out that 50 minus 32 is 18, so 18 equals to 2x. If we divide this equation by 2, if I found out that x equals to 9 units in its length. AN is equals to x equals to 9 units in its length. And JB is also equals to x, it is equals to 9 units in its length. In the next step, I copied the right triangle CJB in a new page and we implemented the Pythagoras theorem on this right triangle CJB. This is the right triangle CJB. This is according to the original domain, according to the Pythagoras theorem. In any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. So in the right triangle CJB, CB squared, that is the square of the hypotenuse, equals to CJ squared plus JB squared. Again, CB squared equals to CJ squared plus JB squared. CB is 41, therefore CB squared is 41 squared, that is 1681, and this equals to CJ squared. CJ is the missing side, so we leave this it is, plus JB squared. JB is 9, therefore JB squared is 9 squared, that is 81. So in total, we found out that 1681 equals to CJ squared plus 81. If subtract 81 from the equation, if I found out that CJ squared equals to 1681 minus 81 is 1600. So in total, we found out that CJ squared equals to 1600. Here we took out of this equation and finally found out that CJ, the missing side CJ equals to the square root of 1600, it is 40. So this is the missing side CJ, this equals to 40 units in its length. CJ is also the height of trapezoid ABCD because it's straight 90 degrees with the two bases. Our test is to find out the area of this trapezoid ABCD. We know that the area of any trapezoid equals to the sum of its two parallel bases. This is, in this case, is DC plus AB times the height CJ over 2. Again, the area of trapezoid ABCD must be equal to the sum of its two parallel bases. This is DC plus AB times the height CJ over 2. DC is 32, AB is 50, CJ is 40 divided by 2. 32 plus 50 is 82, and 40 over 2 is 20, so in total, the area of trapezoid ABCD must be equal to 82 times 20. 82 times 20 is 1640. So in total, we found out that the area of this trapezoid ABCD is equal to 1640 square units in its size. So we finish with the first question. In the next step, I presented to you the second question and resolved the second question by using two different methods. our task in the second question is to find out the area of this quadrilateral ABCD. So in the drawing we have quadrilateral ABCD. This is angle ABC, this is right angle. This is angle ADC, this is also right angle. This is angle BCD, this is equals to 45 degrees in its size. Side AB equals to 10 units in its length. Side DC equals to 25 units in its length. Again, our task is to find out the area of this quadrilateral ABCD. So first of all, we did the construction, that is to say from point B we do perpendicular on DC. Again, from point B we do perpendicular on DC. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point B in DC. This point is point 10. The next step we did another construction, that is to say from point A we do perpendicular on BN. Again, from point A we do perpendicular on BN. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point A and BN. This point is point M. By doing this construction, we did quadrilateral AM and D. Inside quadrilateral AM and D, we have 1, 2, 3 rectangles. The sum of 3 rectangles is 270 degrees, so 270 degrees plus the size of this fourth angle. In total, they must be equal to 360 degrees according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. And therefore, this fourth angle must be equal to 90 degrees in its size. So inside quadrilateral AM and D, we have 4 rectangles. Therefore, quadrilateral AM and D is a rectangle, because it is 4 rectangles. But we also know that the opposite sides of a rectangle are equal to each other. We define side AM as A, so AM must be equal to the opposite side DN in rectangle AM DN. But AM is A, therefore DN must be also equal to A. So this is the form for NC. NC equals to DC minus DN. So NC equals to DC minus DN. So NC equals to DC, that is 25, minus DN, that is A. So in total, NC equals to 25 minus A units in its length. This is the right angle BNC. In the right angle BNC, this angle equals to 45 degrees. This angle equals to 90 degrees, and therefore this first angle must be equal to 45 degrees in its size, according to the rule that the sum of the angles in the angles is equal to 180 degrees. 45 degrees plus 45 degrees is 90 degrees, and 90 degrees plus 90 degrees, it is equal to 180 degrees. That is the sum of the angles in the triangle. We have the rule that says that in front of equal angles in a triangle, there are equal sides. So if we focus on the right angle B and C, in front of those two equal angles, we have those two sides that must be also equal to each other in their lengths. But NC is 25 minus A, therefore BN must be also equal to 25 minus A units in its length. This is the right angle ABC. So 90 degrees minus 45 degrees. The big angle ABC, that is 90 degrees, minus this angle, that is 45 degrees. This equals to this missing angle ABM. Therefore, angle ABM equals to 90 degrees minus 45 degrees, that is 45 degrees. So in the small right angle ABM, this angle equals to 45 degrees, this angle equals to 90 degrees, and therefore this first missing angle must be equal to 45 degrees in its size, according to the rule that the sum of the angles in any triangle is equal to 180 degrees. In the small right angle ABM, in front of those two equal angles, we have those two sides that must be also equal to each other and their lengths. But AM is A, therefore BM must be also equal to A units in its length. What is the length of AN? MN equals to BN minus BM. Again, MN equals to BN minus BM. So MN equals to BN, that is 25 minus A, minus BM, that is A. So in total, MN equals to 25 minus A minus A, that is 25 minus 2A. So here MN equals to 25 minus 2A. In rectangle AM and D, side MN equals to the opposite side AD. But MN is 25 minus 2A, therefore side AD must be also equal to 25 minus 2A units in its length. In the next step, we implemented the Pythagoras theorem of this right small triangle ABM. So I covered the right small triangle ABM and then implemented the Pythagoras theorem of this small right triangle ABM. So this is the small right triangle ABM that I covered from the original drawing. This right triangle ABM, according to the Pythagoras theorem, AB squared, that is the square of the opposite, equals to BM squared plus MA squared. BA is 10, therefore BA squared is 10 squared, this is 100, and this is equals to BM squared. BM is 8, therefore BM squared is 8 squared, plus MA squared. MA is 8, therefore MA squared is 8 squared. So total 100 equals to A squared plus A squared. A squared plus A squared is 2A squared, so 100 equals to 2A squared. And 100 equals to 2A squared. This is quadrangle A, B, and D. And we know that MN is parallel to AD, and after again AM and D, according to the rule, that the opposite sides of a rectangle are parallel to each other. So MN is parallel to AD. But BN is the third line because angle BMN is 180 degrees. And therefore BN must be a third line because any angle that is equal to 180 degrees inside, it is defined as a third line. So BN is a third line. BN is and MN is part of the third line BN and is parallel to DA. So if a part of a third line is parallel to another third line, then the third line itself BN must be also parallel to AD. And because of the fact that BN is parallel to AD, quadrangle A, B, and D is defined as a trapezoid because it has one pair of parallel sides. Side BN is parallel to AD. So quadrangle A, B, and D is a trapezoid. Again, we should find out that quadrangle A, B, and D is a trapezoid because it has one pair of parallel sides. But what is the size of trapezoid A, B, and D? The size of trapezoid A, B, and D, the area of trapezoid A, B, and D must be equal to the sum of its two parallel sides, that is BN plus AD, times the height AM over 2. Repeat again. The area of trapezoid ABCD must be equal to the sum of its two parallel sides, that is actually BN plus AD times the height AM over 2. BN is 25 minus A, plus AD is 25 minus 2A, plus times AM, that is A over 2. 25 plus 25 is 50, and minus A minus 2A is minus 3A. So in total, this expression equals to 50 minus 3A times A over 2. We open the brackets here, we actually found out that 50 times A is 50A, minus 3A times A is minus 3A squared over 2. So in total, we actually found out that the area of this trapezoid A, B, and D is equal to 58 minus 3A squared over 2. Repeat again. The area of trapezoid A, B, and D, in total it is equal to 58 minus 3A squared over 2. Our test is to find out the area of this trapezoid, the area of this quadrangle ABCD. What is the area of quadrangle ABCD? The area of quadrangle ABCD equals to the area of trapezoid AB and D. We already found out that the area of trapezoid A and D is equal to 58 minus 3A squared over 2, plus the area of this right triangle B and C. So the area of quadrangle AB and D equals to the area of trapezoid AB and D, and the area of trapezoid AB and D equals to 58 minus 3A squared over 2, plus the area of this right triangle B and C. The area of the right triangle B and C equals to the base and C times the height and B over 2. Repeat again. The area of this right triangle B and C total is equals to the base and C times the height B n over 2. So in total, the area of quadrangle ABCD equals to 58 minus 3A squared over 2, and NC is 25 minus A. BN is also 25 minus A. So NC times BN is 25 minus A squared divided by 2. We'll open the brackets here and find out actually that the area of quadrangle ABCD equals to 58 minus 3A squared plus 25 minus A squared. 25 minus A squared equals to 25 squared, that is 625, plus A squared minus 2 times 25 times 8, that is minus 58 divided by 2. 58 minus 58 is 0. Then we have minus 3A squared plus A squared is minus 2A squared plus 625. So in total, the area of quadrangle ABCD equals to 625 minus 2A squared over 2. But we have already found out that 2a squared equals 200. Repeat again, we already found out that 2a squared equals 200. Here we already found out that 2a squared equals 200, so we can substitute 2a squared by 100. Here we have 625 times 2a squared, and 2a squared is 100, so this expression in total equals to 625 times 100 over 2. 625 times 100 is 525 over 2. 525 over 2 is 262.5 square units in size. So according to the first method, we found out that the area that we are looking for in this question, that is the area of this quadrangle ABCD, is equal to 262.5 square units in its size. So we finish with the first method. In the next step I presented to you how to find out the area of this quadrangle ABCD according to the second method. In the second method, we did the construction. That is to say, we extended side DA and side CB of this quadrangle ABCD by a straight line until they touch each other at this point. We define this point their touching point as point M. But doing this construction, we already did the right angle MDC. In the right angle MDC, this angle equals to 90 degrees, this angle equals to 45 degrees, and therefore this missing angle must be equal to 45 degrees in size according to the rule that the sum of the angles in the triangle is equal to 180 degrees. 45 degrees plus 45 degrees is 90 degrees, and 90 degrees plus 90 degrees it is equal to 180 degrees. That is the sum of the angles in the triangle. So we'll focus on the big right angle MDC. In front of those two equal angles, we have those two sides that must be equal to each other in their length. So side DC equals to 25, and therefore side MD must be also equal to 25 units in its length. MC is the hypotenuse of the right angle MDC, so MC is an hypotenuse, it is absolutely a straight line. So if we focus on the left side of the straight line MC at point B, here the sum of the angles must be equal to 180 degrees according to Rule 3. Rule 3 states that the sum of the angles from one side of the straight line is equal to 180 degrees. So which angles we have at the left side of the straight line MC at point B? We have this angle that is the right angle, plus this missing angle. In total, the sum of those two angles must be equal to 180 degrees according to Rule 3. Therefore, this missing angle must be equal to 90 degrees in its size. So in the right front angle MBA, this angle equals to 90 degrees, this angle equals to 45 degrees, and therefore this missing angle must be equal to 45 degrees in its size. According to the rule that the sum of the angles in any triangle is equal to 180 degrees. So in the right front angle A and B, in front of those two equal angles, we have those two sides that must be also equal to each other in their lengths. But AB is 10, therefore MB must be also equal to 10 units in its length. What is the area of quadrangle ABCD? The area of quadrangle ABCD equals to the area of the big right angle MDC minus the area of this small right angle ABM. And again, the area of quadrangle ABC in total equals to the area of the big right angle MDC minus the area of the small right angle MBA. The area of the big right angle MDC equals to the base DC times the IDM over 2. And again, the area of the big right angle MDC equals to the base DC times the IDM over 2. Minus the area of this right angle ABM. The area of this right angle ABM equals to the base AB times the IBM over 2. And again, the area of the right angle MBA equals to the base AB times the ITMB over 2. DC is 25, MD is also 25, minus AB is 10, times MB, it is also 10 divided by 2. 25 square is 625, minus 10 square is 100, divided by 2. 625 minus 100 is 525, divided by 2. 525 over 2 is 262.5 square units in size. So in both methods, we actually found out that the area of this quadrangle ABCD is equal to 262.5 square units in its length. Repeat again, the area of this quadrangle ABCD is equal to 262.5 square units in its size. Okay, thank you very much.